visible?
Yeah, we can see everything, so please, screen is yours.
Okay, so good morning, actually good afternoon, everyone. My name is Wiktoria Plechta. I'm a first year computer science student at Silesian University of Technology, and my work was about comparison of neural networks models with GRU and LSTM layers for earthquake prediction. Starting with the short introduction, as the title said, the study was about GRU and LSTM layers, and we compared them for single and two-element prediction using a public available semistic dataset. Shortly about what are recurrent neural networks. They are type of architectural networks that are designed to recognize patterns in sequences of data. Unlike traditional neural networks, RNNs have loops that allow the information to persist, making them particularly well suited for tasks when the order of data matters. And common applications are like time series analyzing, language modeling, and sequences prediction. We choose them for earthquake prediction because earthquakes predictions are sometimes more of random, so it would be more interesting to see how those models work with more random data sets. And however, standard RNNs can struggle with long-term dependencies due to issues like vanishing and exploding gradients. And to address this, advanced RNAs architectures like long short-term memory and granted recurrent tuning were developed, and there will be discussed in this paper. So quick differences between LSTM and GRU. Here we have the visual comparison, and on the left we can see the LSTM cell. It consists of two states, the cell state and the hidden states, and the cell states run straight through the cell with some minor linear interactions, make it impossible to carry information across many time steps. And though this cell has three main gates, the forget gate, the input gate, and the output gate. These gates regulates the flow of information, ensuring that relevant information is kept and irrelevant information is forgot. The forget gate decides what information to throw away, input gates new add information, and the output gates determines the output of each time steps and what to pass on to the next hidden steps. GRU, on the left, we can see the GRU cell. It's slightly different. It contains only two gates, the reset gate and the output gate. The reset gate decides how much of the past information to forget, while the update gate decides how much of the past information to keep and how much of the new information to add. Yeah, moving forward with more differences, but now in list, as I said before, the STM consists three gates, when GRU consists only of two gates. STML is often provides better performance for long-range sequences, while GRU is typically faster. And STML requires more memory to do more complex architecture, but it's better for more complex and longer times data series, while GRU uses less memory, and it's typically better for simple and shorter time series data. Shortly about activation functions and the states, both STML and GRU architectures use the sigmoid activation functions for all the gates, and the hyperbolic tangent function is used for the hidden state, cell state, and candidate hidden states in those cells. Here we can see the hidden, the cell state for the STML function, the hidden state for the LSTM function, and the candidate hidden state in GRU and hidden state in GRU. Those are the equations, and fastly moving on. The database that we used in this experiment, it was the data sets that contain earthquake information from Turkey with magnitude over 40 since 900s. It's available on Kaggle, and we used 4 columns out of 14: longitude, latitude, depth, and magnitude. A 70-30 train split was applied, and the data was used in this rough form without any scaling or normalization, just to observe inheritance, parents, and relationships. The neural architectures, we designed the architectures for both one LSTM layer with 10 units. Also, the GRU model had one GRU model with 10 units. After that, there was a simple dense layer with a sigmoid with a ReLU activation function with 30 units, and the second dense layer with 10 units and also an ReLU function. And the final dense layer had 1 unit to predict the magnitude. The same applied to the GRU model. Number of total params for LSTML was 100,022, and number of total params for GRU model was 1,122, which are quite similar, which was important for this experiment. All params were trainable, and both models were trained using the ADAM optimizer and mean squared error as the loss function. The loss of this small function was suited for a regression task, as it measures the average squared difference between the predicted and actual values, ensuring our model's predictions aligned closely with the true earthquake magnitudes. And we can see the math equivalent of mean squared error here. Shortly about result and curve fusion. The results are shown in 4 graphs for both LSTML and GRU layers for single and 2-step prediction. And first step was to check how the classified is learned from the single data sequences. Here I can just show you both of these graphs. And the results show that in both cases, the mean squared error quickly decreased to a low value. It should be noted that there are small fluctuations in the obtained values, like here. Here we can also see them. This is especially visible in the GRU units, like here. Analyzing the loss function graphs indicated a very small values and a slow decline, and a larger decrease in the values in the loss function is visible in the STM analysis. And it's the most important result coming from this analysis is that both architectures did very well, and the mean squared error is really low. Coming to 2-element sequences, the learning reservoirs are not more stable, as we can see here, and especially here. For the model with LSTM neurons, MSE decreased for both sets. However, the validation set the loss value drops below 0.22 after more than 50 training interactions. A similar situation was noticed in the networks consisting of GRU neurons. However, the decline in this value for this architecture is faster, and the main difference that have been noticed for the network with the STML is that there are no large jumps as for the GRU. I mean, they are quite smaller. However, in network with GRU layer, the values decrease faster than in STMLs. For the rating, GRU classifier achieved a lower value after 100 interactions, which is also worth notice. Coming to the short conclusion, we propose a neural network model using recurrent neurals, specifically analyzing STM, ML, and GRU layers. Both STM, ML, and GRU models achieved very good prediction results, which is the most important factor. It's worth to notice that GRU had fewer training parameters, and STML networks showed more stable error addiction, while GRU networks had larger errors fractation but perform better with 2-element sequences and achieved a lower value after 100 interactions. It's also worth to remember that the dataset rapid achievements of high results suggest a potential risk of overfitting. I think that's all. I would just like to settle this little acknowledgements that this work was supposed by the director's mentoring project Spread Your Wings at the Salesian University of Technology. And thank you very much.
Thank you very much for your presentation. And now we have the last one, live presentation. It will be done